Okay, where we were in this control of breathing was to decide whether it was the DRG or VRG that was the control center that stimulated inhalation, inspiration. We furthermore said that inspiration, as we learned previously in this chapter, is an active process. You have to contract those muscles, diaphragm, external intercostals, and then really for exhalation, it was just passive, let the muscles go. So we need a signal to signal those somatic motor neurons to breathe. That is what we're going to call a ramp signal. We think now it comes from the VRG. We think now it comes from the VRG and sends signals from the VRG into the somatic motor neurons. Okay. Now, let's think about that. Normal breath rate is 12 to 18 breaths per minute. That's normal. 12 to 18 breaths per minute. That's the normal. Actually, and I should say 12 to 20 breaths per minute is the normal. Some will say 12 to 18, but 12 to 20. Now, I'm going to take it at 12. Let's say for demo purposes, we're going to take it at 12. All right. Now we're to what we talked about in the previous one, the I to E ratio. Go back to a previous video on the I to E ratio, the inhalation to exhalation time. All right. If we take it, and this is what we had, you can go back and you can see in your list of videos where that is. If we take it as 12, then that would mean 5 seconds per breath, right? And we said about 2 seconds for in and 3 for out. But we said the ratio 2 to 3 is true even if it's 20 breaths. It would just be a different time, but it would still be the same ratio. We said that the exhalation time is really almost equal to the inhalation time, but there's a moment when you breathe that you don't do anything. And then you exhale, and that counts in the exhalation time. All right. So now we're looking at this ramp signal, okay? This ramp signal. Now, what is this ramp signal? Inspiratory ramp signal, nervous signal that's transmitted to inspiratory muscles. Remember that's the diaphragm, external intercostals, mainly the diaphragm. Is not an instantaneous. Begins weakly and increases steadily in a ramp manner over about 2 seconds. And now that's if we're doing 12 breaths per minute. Eupneic breathing. Stops abruptly. So it increases. Now when it increases, what it really means, increase in the frequency. Remember, action potentials are all or none. So this increase is an increase in the frequency of firing through those neurons. Increase in the frequency of firing. Then all of a sudden it just stops. And when it stops, that's when you do your exhale. So inhale, exhale, inhale again. Stops abruptly for about 3 seconds, turns off the excitation of the diaphragm, and again it begins again. Now that's if that 3 seconds is if we're doing 12 breaths per minute. But the main thing we're saying is that's what it does. Now, here's the situation though. Okay. Now, first of all, why a ramp signal? Why do you need an increase in frequency of firing? Start slow. Okay, now I want you to think about this. If you're blowing up a balloon, you start blowing into it. For a while, once you get it going, it's going to be real easy. It's stretching. But as you get to where the elastic part is getting close to no longer there because you've stretched it too much, you've got to blow harder. What do you have to do? You have to blow harder. So therefore, what happens is that when you first start inflating those, you can inflate them, provided now that you got adequate surfactant and a nice positive expiratory peak pressure. Remember that residual volume? If you don't have that, then it's going to be hard to inflate them. But if you have adequate surfactant and they haven't come in too far because you left air in there, we talked about that, then you'll do it. But as you start to increase, it starts to get a little tight because those elastic fibers in the lung, Remember, the elastic fibers, the surface tension of water and the elastic fibers contribute to the compliance of the lung. That's how that comes in. So those elastic fibers get stretched a little bit, so you got to have a faster frequency to keep going, and then finally it's over. All right. But that's not completely the case. Okay, now listen to me. You see this 2 to 3. All right, now this is where the clincher is going to come in. Now, we're saying the VRG is doing this. Old people, the older thing was the DRG. But let's say now I'm going to throw in this boy here. Technically speaking, I'm going to come back here. Technically speaking, the VRG, or even if it was the DRG, would like to keep going further. Now listen to me. The VRG, or old days the DRG, would like to keep the signal going longer. Now, the longer it goes, the more you blow up the lungs. And see, we don't want to over-distend the lungs. Now, it might want to go 6, 7, 8 seconds. Now, let's think about that. If it went 8 seconds, okay, then it's going to take more than 8 seconds to blow it out because it's a 2 to 3 ratio. That means all you're doing pretty much is about 2 breaths a minute, and that's certainly not enough. So what does that mean? That means you're going to have to slap the hand of the VRG, make it stop. That is the role of the pneumotaxic center. That's the role of the pneumotaxic center. Let's go here. See, it's negative. It sends an inhibitory postsynaptic potential to the VRG, old days DRG, to cut it off. It antagonizes the DRG and VRG, inhibiting the depth of respiration. The pneumotaxic limits the burst of action potentials in the phrenic nerve. Remember, the phrenic nerve was the one going to the diaphragm, effectively decreasing the tidal volume. Remember, in that time frame, you're bringing in about 500 cc's when you put everything together. Absence of this pneumotaxic center, or the pontine respiratory group, PRG, pneumotaxic is one of them, results in an increase in the depth of respiration and a decrease in the respiratory rate. Okay? So really, when you think about it, the two main centers in the brain that are working is the VRG and pneumotaxic, and maybe some of the DRG. Okay? All right. Now, we brought up this other one called the apneustic center. The apneustic center is questionable. The apneustic center is a center that's supposed to stimulate the VRG if it tries to go a little wacky, shall we say, doesn't want to work. It's trying to prevent apnea. Apnea, that's cessation of breathing. The reason we aren't sure about that is because you do have sleep apnea and other conditions of apnea. So it's present, we believe, but doesn't seem to be working that well. Now, we know in lower forms of animals, it seems to be doing pretty good. But in the human, it seems to be selected against evolutionarily. But anyway, we list it. Okay? We list it. All right. Now, let's go a little further now. All right. That's the motor side, ladies and gentlemen. That's the motor side. Now, how do you know when to do this stuff? When to increase breathing and decrease breathing and all that? See, that's where these sensory inputs came in. But the one we said that was the physiologic one was the chemoreceptors. So that's where we want to go now, are the chemoreceptors. The chemoreceptors, okay? Now, in the chemoreceptors, you have central chemoreceptors and peripheral. We want to address both of those. The central and the peripheral, okay? So we're going to come here, and I'm going to start first with the central chemoreceptors, okay? Now, the central chemoreceptor, I'm going to say, is located, so we're going to say the central chemoreceptor, I'm going to come back here, is located about 1 millimeter below the ventral medullary surface. Okay, let me say it again. The central chemoreceptor appears to be located about 1 millimeter below the ventral medullary surface, up in here. That's where it appears that central chemoreceptor is. That's in the brain. Now, remember, the brain is surrounded by cerebrospinal fluid and also by a blood-brain barrier. So I want you to keep that in mind, that you got the cord, you got the brain and the spinal cord, but there's cerebrospinal fluid around it there, okay, because you got the meninges. Remember the meninges? You had the meninges. In the subarachnoid space of the meninges, that's where your cerebrospinal fluid floated. In the subarachnoid space, that's where your cerebrospinal fluid floated. Okay? Then, surrounding capillaries in the brain is something called the blood-brain barrier. What is it? The capillaries are continuous type with fortification by tight intercellular junctions and surrounded by astrocytes. Of these coverings, all of these coverings are primarily lipid in nature. Water-soluble charts have difficulty going through, like H+ protons. Carbon dioxide can easily go through. So I want you to think of the cerebrospinal fluid and the surroundings around the capillaries as we approach this. Now, that is true when we look at the central chemoreceptors. The central chemoreceptors. Okay? All right. So what I want to do now, we talked about the motor side. Now I'm going to close this video and we're going to do the sensory side in a fresh video. The sensory side.